Hey there, my name is Alejandro and welcome back for day 26 of me doing the Daily LeetCode challenge until I reach 1 year's worth of green contributions here on GitHub. So today's problem is for August 11th, 2024, and let's get straight into it. Okay, so today we get a LeetCode hard problem 1568, minimum number of days to disconnect island. Okay. You are given an n by n binary grid where 1 represents land and 0 represents water. An island is a maximal 4-directionally horizontal or vertical connected group of ones. This grid is said to be connected if we have exactly one island. Okay. Otherwise, it is said disconnected. Okay. So like number of islands. Okay, sure. In one day, we are allowed to change any single land cell 1 into a water cell 0. Return the minimum number of days to disconnect the grid. Oh, with a day being what? Okay, in one day, we're allowed to change any single land cell into a water cell. Okay. Number of days to disconnect the grid. To disconnect the grid. And it's disconnected. So it's connected if we have exactly one island, right? Otherwise, it's disconnected if we have not exactly one island, right? So exactly one means, so that it's disconnected if we have less than one or greater than one. So, okay, there's three cases. Case 1, less than one island. Case 2, exactly one island, connected. And case 3, more than one island. Okay, so we want the minimum number of days to disconnect the grid. Okay, so let's look at an example. So here we have 0, 0, 0, so everything except here. So okay, here we have exactly one island, right? Okay, yeah, and here, so if you make these two water tiles, then, okay, the island is disconnected, right? Because, okay, it's 4-directionally horizontal, vertical, just like this. Okay, makes sense. So, okay, the output is 2. We have to make these. Yeah, okay. So if you made any one of these water, you'd still have 3 connected ones. Then if you make 2 of them water diagonally, then, okay, you have 2 disconnected ones. But if you chose 2 vertically or horizontally, then you would have still had 2 connected ones, and therefore you'd still have one island. Okay, that makes sense. Here, okay, so you just have 1, 1. Okay, but you still need 2 because you're gonna, okay, you need to make everything water. Right. So if grid, so we could, okay, we could do something similar to 2 days ago where we handle the case where everything is a row, or handle the case when you just have one column, so one row or one column, and then handle the case when you have more than one row and more than one column, right? Just as little base cases. Well, let's try to think about this problem. So first of all, okay, let's not care about efficiency. Let's care about problem solving, because this is a LeetCode hard, and I don't want to get stuck. So this is an optimization problem. It's a minimization problem. So we can always resort to something like greedy, divide and conquer, or dynamic programming. Usually, not always the case. So I don't want to make the mistake again, where last time I did a LeetCode hard, it was an optimization problem. I was super set on using greedy, divide and conquer, and dynamic programming, and ended up wasting too many hours without having. I think the solution was to use BFS, and I was like, goodness. And so I don't want to be too rigid in tunnel vision on using one of those algorithms. But it is technically a minimization problem, so we can resort to one of those algorithms if need be. One of the very first things that we can do is, well, we can call minimum number of islands, right? No, we can call number of islands. So we can first find out the number of islands, right? There's a famously, so it's kind of like yesterday's problem where we already coded up a number of islands solution. And so we can first get the number of islands, and if we have exactly one island, so if the number of islands we return is 1, then that means we need to disconnect the graph. Otherwise, it's one of these two cases, and we automatically can return 0. So let's create a helper, first of all. Let's just say number of islands, self. And you know what? We're going to say self.grid is equal to grid, number of islands. Actually, we're going to say if self.number of islands is equal to 1, or doesn't equal 1, then we're going to say return 0, right? You have either more than one island or less than one island, in which case you're disconnected, right? Graph already disconnected, so return 0. There we go. Okay, and here we're going to do def underscore init self.grid is equal to none, and then we initialize here self.grid with this, and so here we can make use of self.grid. Okay, perfect. So number of islands. Okay, I mean, since I just did this yesterday, this will be very simple, but I think we can just do something like directions. We have -1, 0, 1, 0. So let's think about it this way: up, down, left, right? So if you increment by 1, you go down. So decremented means you go up. If you increment by 1, then you go down. Now for the columns, if you increment by 1, you go towards the right. So we want -1 for left, and then 1 gives us to the right. So that's kind of the idea here. And then we can make a function here, def is out of bounds self, and we're going to take an I, j, return 0 is less than or equal to I is less than length of self.grid, and 0 less than or equal to j less than length of self.grid at index I. Okay. So for direction in directions, we're going to say, actually, we're going to say, okay, first we're going to go through for I in range length of grid, of self.grid, for j in range length of self.grid of I, we're going to say, first of all, we want to count the number of items. So we only care when the grid value is 1, right? So if grid of ij is actually equal to 1, and self., and not self.is, so, or is inside bounds, is in bounds. Then we want to call we just ideally okay, we shouldn't do what we did yesterday, where we set all the values to 0 here, right? Where it's like because we're still going to need access to self.grid, self.number of islands, we're still going to need access to our grid in case the number of islands is equal to exactly 1, right? So let's just use a visited set instead. We can even do this. Self.visited is equal to a set. And here we're going to create a function, def visit all land neighbors. We say self I, j. We're going to say, so this is the one where we're going to need the directions. We're going to say, okay, for direction in directions, we're going to say, okay, new I, new j is equal to, first of all, we're going to say delta I, delta j is equal to direction. New I is equal to I plus delta I, j plus delta j. Right? And then we're going to say if self dot is in bounds, new I, new j, and self dot grid of I, j is equal to 1, then self.visited.add I comma j. First of all, here we're going to do self.visited.add I comma j, and self.visit all land neighbors from I comma j. Then, okay, so we added it to the visited set, and then we want to call self.visit all neighbors. Visit all land neighbors from new I comma new j. And here we want to do new I comma new j. Self.isInbounds new I new j, and self.grid of new I new j is equal to 1. Then it's a land, so we want to add that to visited. So first of all, assert new I comma new j actually, we're not going to add an assert, we're actually going to make this another and statement. And not and new I comma new j not in self.visited, and it's equal to 1. Then we're going to add it to the visited and visit all of its neighbors, right? And then from there, return. Here we can say, okay, return 1 for now. I just want to make sure that it creates the number of islands. Okay. Actually, for now, we can just say return self.number of islands, right? Just to test. Maybe print self.grid, print self.visited. So let me just check here for I, for j. Yeah, if grid of I, j. First of all, you don't need that. These are all in bounds. So okay. And I comma j not in self.visited. Yeah, there we go. Okay. Okay. It should be good. Let me see if that returns me the number of islands. Oops, where did I make the mistake? Self.grid. What? Oh yeah. Number of islands is equal to 0. Visited.add this, self.visit all land neighbors, and then number of islands you've seen plus or equal to 1, and then here return number of islands. Okay. So here this is good, right? So okay, this one only had 1 island, this one only had 1 island. Here we're returning 1, and here we're returning 1. But maybe we can try it on a more complex grid. Otherwise, this should be working, right? So yeah, you have number of islands, you go through everything. If it's equal to 1 and you haven't visited yet, that means you are visiting a new island. So populate self.visited with all members of that island, and the number of islands plus or equal 1, and return number of islands. And visit all neighbors, yeah, so for direction in all directions, take the new I, new j. If it's inbounds, not visited, and it's equal to 1, that means it's in the same island, and it's not been visited, so add it and visit all neighbors. Okay, and inbounds is good. Okay, so that's good. So one thing I'm realizing now and that we can leverage is, first of all, if the number of islands is not equal to 1, then we return 0. That's GG, right? So of course we're not gonna do this. So that's the case 1 and case 3 here, right? So if it's not equal to 1, Remember, a graph is connected if and only if it has exactly one island. So if it doesn't have exactly one island, because we just counted the number of islands, then we return 0. Otherwise, we have exactly one island. And the nice thing here is that this self.visited will be the positions of every element on inside that island. So maybe we can now use, so that's why I created a self.visited instead of a normal visited set that I passed through the function. So that way now we know that all of these elements pertain to the same island. And so maybe we can use these elements in a certain way to kind of figure out the minimum number of ways that it will take in order to split the island, right? And to split the island, they didn't say if it takes something like, do you have to split the island in half, or so you're given an n grid where an island is a maximally forward direction group connected of ones. The grid is said to be connected if we have exactly one island. Okay, otherwise it's disconnected. In one day, we're allowed to change any single land cell 1 into a water cell. Turn the number of days to disconnect the grid. So one thing, okay, I was thinking about an idea, but maybe it only works if you have a squarish shape. Or it's like here what I noticed is that like you put 2, right, and you disconnected these 2. But what if you had something like a 3x3, right? So you have a 3x3 of ones like this. If you just changed this to water and this to water, then all of a sudden this one is not connected, right? And it doesn't matter how many ones were here, right? But maybe this only works with square shapes. Or well, it would work with rectangular shapes, right? Here you still have the 0 and 0. But then again, it doesn't have to be a rectangle, right? There can be no element there can be no element here, there can be nothing here, and so on. I mean, here you can still do the 0, 0. Oh. No, but this is a LeetCode hard. There's no way it'd be that simple. There's no way. Or, so what would be a counterexample? Okay, so we can't change that one to 0 because then we'd have 2 islands and we would have returned. Well, surely there's a counterexample here. So my idea was like maybe you only, yeah, no, that would probably make the problem way too simple, right? Like if you could cut off like maybe like, well, okay, it doesn't have to be. First of all, okay, maybe something like this, where it's like it'll be constrained to the height or the length of the island, right? Because one thing you can always do is you can take this, like for example, this island, you can just cut off one of the heights elements here, right? Like you set this to a 0, a 0, and a 0, and all of a sudden, boom, you have 2 disconnected islands. That's like, okay, so let's think about it. Since this is an optimization problem, so we can always resort to something like greedy, divide and conquer, or dynamic programming. I doubt divide and conquer is kind of like the islands can be kind of anything. So I don't know how we'd split this into like subproblems, like a fourth, a half, a third of the size, and so on. So we can first try to think of a greedy solution, and then if that doesn't work, we can try to think of a dynamic programming solution. So let me think. So a greedy solution would be like you try to find like a cornermost one, right? So it's like this is a cornermost one, this is a cornermost one, this is a cornermost one. So this one, like for example, you could just set this as 0 and you already have a disconnected island here. So let's think about, okay, so let's think about all the possible cases, right? You have a cornermost one. So first of all, you could have a 1 that is surrounded completely by 1s, right? Here, it would take, oh, wait, so what if the maximum of this problem is like 4, right? Because it doesn't matter what one you pick, you can always make the 4 around it zeros, if they even exist. I wonder, okay, I wish they kind of gave us more examples here. -30, yeah, okay. Wait, one thing I'm realizing is, okay, if you have if a 1 is surrounded by just 1s, you only have to change the 4 around it, and then that one is straight up disconnected from any other possible island that could exist in the graph. So you could literally pick any one. Okay, so this is definitely going to be more greedy than dynamic programming. Wait, am I understanding the problem right? You're given an n by n binary grid where 1 represents land and 0 represents water. An island, yeah, connected group of ones, like just, it's literally number of islands. The grid is just said to be connected if we have exactly one island. We are allowed to change. It's just this feels like it would be too simple for a hard. Okay, maybe okay, we should also go through the other cases. So what if so okay, so this is nice and sunshine and rainbows. What if we have something like, first of all, in this case, well, again, the minimum number of ones here would be just do these two and so on. I'm trying to think. Okay, so if you have a 1 surrounded by 4 ones, well, the minimum in this example would be like you destroy the middle one. So you want to like destroy the one that's like connected with the most number of ones. Maybe that's like the greedy approach, and then it's like you keep doing that, and you kind of reach your minimum number of days, because you kind of have like the most destructive effect every time, right? Like if a 1 is connected with 4 ones, then you just like you kind of separated the island as much as you possibly could. But then okay, if you have a 0 here, then okay, it just takes 3. Then if this one is a 0, then it just takes 2. Well, in this case, actually, okay, wait, no, that changes. All of a sudden, this middle one, you change it, and it doesn't matter what's, actually no. What if there was another row here and there's just ones connecting the two? Okay, but one thing for sure is that the max value for this problem is 4. So I think we're discovering something interesting here, where if you have a 1 surrounded by ones, then you can just straight up set all 4 of the ones next to it. So maybe we want to find the least connected one, right? The one in the graph that is leastly connected to the number of ones, right? So maybe inside of this visited set, okay. So if a 1, okay, so a singular 1 is connected to at most 4 ones and minimum 0 ones. 0 ones. If 0 ones, then we have more than 1 island. So impossible. So every 1 in the island is connected to 1 to 4 other ones. So my idea is, okay, what if we find the one with the minimum number of connections to other ones? If minimum is, oh, but that doesn't work, right? If you like actually no, there's so okay, I was gonna say, what if the minimum is always 4, right? But can that even be possible? Well, it's like if every element needs to be connected by 4 ones, that means it needs a 1 above, below, to the left, and to the right. But then it means that this one also needs 1 to the right, 1 above, and 1 below. But then it means this one also needs 1 to the right, and 1 above, and 1 below, and so on, and etc., etc., etc. And so you go on to infinity. So you can't have, So like it can't be that every single one has a 1 to its right, right? Because that means you'd have an infinitely long sequence of 1. So, oh, if everyone must have 1 to its right, then this one must have 1 to its right over here. But this one must have 1 to its right. But this one must have 1 to its right. But this one must also have 1 to its right. So it can't be that every single one has a 1 to its right. At some point, you hit a border. So there will be at least one 1. So there will be at least one 1 that doesn't have a 1 to its right. Similar for top, down, and left. But now is it possible for... It can't, no, it's not possible for every 1 to have 3 1s next to it, right? Because you might, so this one might be the rightmost one in the entire grid, but then it's like, if you want every 1 to have a 1, 3 1s, then this one needs to be at 3. It needs to have 3 connected ones like this, right? But then, oh no, but this one could have a 1 to the... Okay, but what if, okay, no. Let's think about the, let's assume that this is the most right one, right? There must be someone that's at the most right of the entire grid. It could be way up here. It could be like, here's a 1, and 1's over here as well, right? It doesn't have to be this one and so on. Like, there's someone that is the rightmost in the entire grid. Then from that 1, if every single 1, if there might be more than one rightmost one, right? You take the rightmost one, but then is it the same argument for the top and bottom, where it's like rightmost and bottommost one? So at some point down this chain of the rightmost ones, you're gonna have one that's at the most bottom, right? Because you can't go infinitely. At some point you hit a border. So you'll have at least one 1 that is no 1 here and no 1 below. So the idea is, okay, if you take the rightmost one in the entire grid and then find the bottommost one inside the column that the rightmost one is in, then that 1 doesn't have a 1 to its right nor below it, meaning it can only at most have a 1 to the left of it and above it. Okay. If this works, this is definitely a greedy problem, right? Okay. Meaning it can only have at most a 1 to the left and above it. So this means that the real minimum and most, this means that, no, there exists at least one 1 such that the maximum number of 1s that it is connected to is 2. And of course, since the number of islands is exactly 1 in this case, so by the way, I write this down because it's like it helps me write down my thoughts and so on, so that like there's so many things going on in my mind, and I just write everything down and just poof like this. So okay, and of course, since the number of islands is exactly 1 in this case, there must be at least 1 attached to the one that we this such one with at most 2 attached ones mentioned above. Okay, so my idea is we're gonna greedily find the one that's rightmost. It could have been leftmost and then upmost and so on. It doesn't matter as long as we fix a cornermost one. That was the original idea. So we could either do leftmost and upmost or downmost and so on. The idea is like pick a direction you want to go, right? Northeast, northwest, southeast or southwest, or like top left, top right, bottom left. Right now I was just thinking like think of getting the rightmost one, and then that rightmost one in the grid will happen at a certain column. Inside of that column, find the bottommost value inside that column that also has a 1. Then it must be that since it's the bottommost one, there's no ones below it, and since it's the rightmost one, there's no ones to the right of it. So ones can only be to the left and above it, and there must be at least one either to the left or above it, because there's only one total island, because in this case we've already checked that there's a 1 island, right? Let's get rid of this return. Okay. This is good. So okay, this is a greedy problem if this works. Let's capitalize this A. Okay, so step 1, find rightmost one. And so the way we're gonna do this, okay, I'll just keep this drawing for now. Step 1, find rightmost one, right? And so what does rightmost one mean? So find column of rightmost one. So we have this self.visited set over here, right? We want to find the rightmost one, and specifically the column it belongs to. And so inside of this visited set, we're gonna have pairs of I, j, where I is the row number and j is the column number, right? So we want to find in visited the max element where the key is this. So I wonder, does max take a lambda function? If I do something like this, Python 3, let's create a set with values like, let's do import random. We're gonna say set of this random.rand int 1, 219 random.rand int 3, this, like that, for in range 100, and we're gonna call this s is equal to this thing, so s, okay. And now we're gonna say max of s, where lambda x is gonna be x of index 1. Yeah. S equals list s. No, key is equal to this, right? Okay, s equals set s. Okay, and I trust this, right? Max is equal to max res is equal to float negative infinity for element in s. If L of 1 res equals max of L of 1 comma res, yeah, okay, 12, okay, so that works. So we can do this. So we're gonna do row comma call is equal to max of self dot visited. So row comma col is equal to 0 comma 1. So these are constants. We're going to say row underscore comma j max of self.visited with key is equal to lambda take a pair and return chord and return chords column, or maybe position. There we go. So J okay, we can call this rightmost column. It's fine, J. Actually, rightmost column. Okay, now we have the rightmost column. We want to find the deepest one, right? So deepest row is going to be equal to 0. How does filter work again? Okay, we're just going to say for I comma j in self, for pos in self.visited, I comma j is equal to pos if deepest, if j is equal to rightmost column and self.grid of ij is actually equal to a 1. Actually, they must be, right? They're in self.visited. And if j is equal to rightmost column, deepest row is equal to max between deepest row and I. Right? So now we have step 2, find deepest one inside column from step 1. Now step 3, this one has at most 2 1s next to it and at least 1 1. Next to it. Okay. So, case 1. Only one neighbor 1. Case 2, 2 neighbor 1s. So in this case, okay, so first of all, we need to get left pos and top pos. Left pos. Okay. So again, we know that so here we've gone through the rightmost column where there are 1s, and we find the deepest one, right? So we know there is no 1 to the right and below, but now we need to check the elements to the left and above, right? But it could have been that our deepest one was let's say was the top right corner, or let's say it was the top left corner, right? There's only 1 1. That's like there's nothing above it, nothing to the left of it, and so on. So first of all, if not left pos is equal to so we're gonna have deepest row and rightmost column, right? And so left position means you wanna decrement a column, right? So you do this. North pos or above position is equal to deepest row minus 1 rightmost column. So first of all, if dot is in bounds left pos, if not self dot is in bounds left pos, or not self dot is in bounds right pos, there must be exactly 1 1. So if self dot is in bounds left pos, assert self I comma j is equal to left pos, assert that self dot grid of I comma j is equal to 1. And then we're going to say, okay, so if we fill that 1 with water, if we change that 1 with water, then all of a sudden we know that there was only exactly 1 1 that was next to it. We just filled that 1 that was next to it with water, therefore that island is not completely separated. So now we return 1. Otherwise, assert self dot is in bounds right pos, assert same thing, where I comma j is equal to right pos, and return 1, right? Otherwise, they're both in bounds, right? So the idea is, okay, we have this rightmost and deepest most 1, right? If it's the case that either the element to the left or above it is out of bounds, well, first of all, we know that there's at least 1 1 that's next to it because we only have 1 total island, right? Wait, what if it's the only element? Okay, let's just do a little check. First of all, okay, if length of self dot visited is equal to 1, then return, we just make that 1 water and we return 1, right? Okay, so let's just do that. Okay, now there must be at least 1 1 next to it, right? Because there's more than 1 1 inside the total island that we have found, because again we just handled the if there's only 1 element case. So okay, so now there must be exactly 1 1, because it's either the case that left pos or right position above or to the left is out of bounds, which means that the one that's not out of bounds must be so I'm just gonna say assert, yeah, okay, well, not self dot is in bounds right pos, right, so it's like it's so what am I saying? Oh yeah, okay, so the idea is like we know that there is at least 1 1 that's next to it. So at least one of these two, the left or the right, must be in bounds, right? And so if at least one of them is out of bounds, okay, so if left is in bounds, then that means that's the one that must have the 1, right? So I'm making these assertions for sanity check. But otherwise we just return 1, right? Because we take the neighboring one, we replace it with water, and all of a sudden we have a disconnected island, right? It is rightmost, deepmost, there's only 1 1 that's connected by it. Destroy that 1, and now you just return 1. Otherwise, again, if it's the upmost that happens to be in bounds, then just set that one to be 0, and then like now you have 2 total islands, and so you just do that. So this is very much a greedy problem. Otherwise, yeah, so assert, and so assert that they're both in bounds if grid of left pause row, left pause call doesn't equal 1, return 1. Same thing with right pause. Right, so it's like if so this one has an element to the left and above. If the value of either of them is not 1, that means there's only one adjacent one. And so by the same argument, you say that you just delete the adjacent one, and now you only have one island left, right? So the idea is that like we have this, essentially we have found this deepmost rightmost one where we know to the right of it and below it are non-1 values, right? So the only placeholders that could have a 1 are here as well as here, right? And so here it's like, okay, it could be that there's 2 1s, right? If one of these positions, first of all, is like out of bounds, that means there's only 1 1, right? And so we can delete that 1 by replacing it with 0, and then for sure this 1, now there's no 1 to the right of it, no 1 below it, no 1 to the left of it, no 1 above it. So therefore it's its own separate complete island now, a 1 1 island, but now it'll be disconnected from any other island that was before it. Oh, the only thing I have to think about is this case 2. Okay, you know what? We're also going to do if length of cell dot visited is equal to 2, then return 1. Return 2 actually, right? Because the advantage is if you have 3 1s, right? The idea is you can leverage the fact that you can make this a 0, and now this is an island of itself, this is an island of itself. But if you only have 2 1s and you make one of these a 0, this one, yeah, it's disconnected from any other 1s in the whole island. But there are no more other 1s, right? Because they were the only 2 1s that exist at the beginning. So now this one has to be deleted as well. And obviously, if we only return this case if there was 1 total island. So and self-visited is a number of the locations of each element inside the island. So we know if there's exactly 2, they are connected, and we need to delete both of them. If there is just 1, then you just get rid of that one. So these are the base cases. Okay, so good thing we thought of that. Otherwise, so there's only, so this is the idea. If they're both in bounds, right? But let's say just even one of them is a 0. Wait, no, it's minimum 1 first of all, because yeah, there's an island, so at least one of them must be a 1, right? So let's say without loss of generality, the left one is a 1, right? And now we know that both of these are in bounds, and we don't know what's above here. If this value happens to be a 0, well then we just delete this one right here, make it a 0, and this one's completely disconnected, and then we're done with the problem. So if this one is a 0, we only have to delete this one here, right? Versus if this one was a 0 and this one was a 1, then we just get rid of this one, and now we have this disconnected island right here. So if either of them is a 1 and the other is 0, right? So if any of them is not equal to 1, then we return 1 because we just delete one thing. Otherwise, this is the case where it's 1 and 1. Here we would have to delete 2. Okay. But here's the problem, right? Here we would have to delete 2. But what if the top leftmost one only required 1 deletion? We're not gonna have a complete problem yet, right? We're actually gonna fail here. So let me do something like this. Otherwise, return 2. To do what if can disconnect island somewhere else with just 1 cut. So we could just do a for loop. I'm pretty sure if we cover all four corners, we might be able to do it. Because I'd have trouble seeing where else you could do it, right? Where it's like if you do it on the leftmost column, then if you don't get the deepmost one or the upmost one, it's like what are you doing? You're just wasting like resources. So the solution will inevitably have to be at one of the four corners. It's just it might not be the bottom right one as I'm doing right now here. So that's something good to read. Okay, well, first of all, we can test this. Okay. Yeah. Let's get rid of this. Actually, yeah, okay, well, once we get rid of these little errors here, it's equal to 1. Of course, of course, of course. Yeah, I wonder in Python, can you do something like this? 1, 2, and then if I do this, can I? No, I can't. Not inside yeah, that's not gonna work. Yeah, so 0 or row. Call. So we're gonna say like this, if not. Right pause row, right pause column. Oh yeah, above pause, sorry. Oh goodness. Line 83, above pause. Okay, self.is in bounds. There we go. Above pause, above pause. Do above pause, above pause. This, and then above pause, above pause. Okay, now run. Oh goodness me, above, so first of all, we're gonna change all of these with above pause here. Okay, but now if I submit this, I actually expect it to fail. I just want to check. Okay, yeah, so okay, this is what I expected. We pass a crap load of test cases, and yeah, exactly. So I output of 2 and expected 1. Okay. So I think we actually have a right idea for this problem, which is great news, first of all. Okay, so this is a greedy problem. Again, whenever you face an optimization problem like this, I didn't want to make the mistake because technically I was proven very wrong when I did a LeetCode hard last time. Which, first of all, if my idea works here, like this is not this LeetCode hard isn't too hard, but whenever you have to solve an optimization problem, a lot of the time you can solve it using either greedy, divide and conquer, and dynamic programming. And usually divide and conquer is not that too common, right? But usually, like optimization problems, you can solve with one of those algorithms. But again, I was proven wrong last time when I did a LeetCode hard, where it was a LeetCode hard optimization problem that was solved with BFS. And so it's not always the case that you can just slap one of those algorithms for like the cleanest, most elegant solution, but a lot, like 95% plus of the time, whenever you solve an optimization problem, you can use one of those three techniques, which is why I kind of resort to them like almost like automatically whenever I see an optimization problem. So in this case, this problem is a greedy problem, right? So the idea is that you want to disconnect islands, and you're kind of trying to find like the least connected one, so that like you could just cut off the like connected ones and make it its own little island itself, right? It's like it's a greedy solution. You try to like find the least connected one. So one way we could do it is essentially whenever we do number of islands, instead of using a visited set, we could put a dictionary, and inside of the dictionary we take in the number of ones that are adjacent to it, right? Oh, and that wouldn't even limit us to the four corners idea. Wait, actually, we can totally do that. That might even be more cleaner. Or even cleaner, sorry. First of all, self.visited, if I change this to a dictionary, does it work like a set in that I can, yeah, so, okay, so dictionaries don't have an attribute add, but at least I'll, yeah, okay, self.visited.add, we're gonna say def get num adjacent ones self and a position I, j. And here we're going to say direction equals this. Again, this is going to be all O of one work. This is all O of one work. So we're going to say for direction in directions, di dj is equal to direction, and we're going to say new I, new j is equal to I plus di, j plus dj, and we're going to say if self.is in bounds new I, comma new j, first of all, and self.grid of new I, new j is equal to 1, then num ones, first of all, is equal to 0, num ones plus or equal 1, return num ones. We don't even have to do the, for now we can do the over and work with the dictionary, but we can also just keep track of the one with the least connection of ones, right? But otherwise, okay, for now let's make our life easy. Whenever we see a self.visited add, we're going to say d of I, j equals self dot get num adjacent ones I, j. Visited.add. We're going to say d of new I, new j equals self.get num adjacent ones new I, new j. Actually, self.visited. Whoops. Self.visited I, j. So you can do something like that. Right, very cool. Then we can even scrap all of this logic here, right? Where it's like, So yeah, at least 1, 1. And of course, since the number of islands is exactly 1, there must be at least 1, 1. So we have the minimum number of, we can use, so we're going to say minimum of d.values, or self.visited.values. This is the number of adjacent ones to the one in the island with the fewest number of ones adjacent to it. Again, this number must either be exactly 1 or exactly 2. No more, no less. If min of self dot, so okay, so case 1, this is a 1, in which case the answer you return is going to be 1. Okay. Assert 1 less than or equal to min less than or equal to max less than or equal to 2. Okay. And now this minimum of self values. So yeah, so if the minimum is 1, then that means you just have, there exists a 1 such that the number of adjacent ones to it is exactly 1. So you can cut off that adjacent one, and this one will only have no more adjacent ones next to it, so it's connected from the rest of the island. And again, we've already handled the base cases when there is just 1 or 2 elements total inside the only one island, right? And then otherwise there's one that has 2 ones next to it. If that's the minimum, then you just have to invest in either doing 0, 0, and so on. But one thing that we will know about this value is that it's going to necessarily be one of the 4 corners inside of the so like inside where the corners means like it's either going to be, so there are only 4 possible values of ones that will have that minimum value, right? Or like if you checked all 4 of those ones, you will get the optimal solution. So the first idea is in the rightmost, so find the rightmost column in the grid that contains at least 1 1 in it, and then inside that column find the topmost one and the bottommost one, and then same with the leftmost column that contains a 1, find the topmost and bottommost one, and so on. The idea is that those ones have at most 2 connected ones, right? And every other one might have between 2, 3, and 4 connected ones, but those 4 have a maximum of 2 connected ones, and so you can just slash off the 1 or 2 ones that it's connected to, and then you create a separate new island entirely from that one. And so yeah, but in order to make our life easy, what I realized is like for each one that we visit inside the number of islands call, just keep track of the number of ones it's adjacent to, and then get the one that's the minimum, that has the minimum number of adjacent ones to it, and then just like use that value to return how many days it will take to turn ones into water to make that singular one separated from the other island, right? So let me go back here to my code. Yeah, so if the value is 1, then you just cut off 1. Otherwise, if it's 2, it's 2. So we're actually just going to return this value here. Return this. Yeah, I think this would work. Really? Oh, wait, of course. This isn't considering the 4 corners, right? For the 4 corners, this will be true, but not for every other 1. But we can definitely assert this for the minimum one, right? No. 94. Interesting. Okay, so maybe this is a LeetCode hard for another reason I didn't realize. So let's go right where we were. So this is 1 1 0 1 1 1 1 1 1 1 1 0 1 1 1 1 0 1 1. Oh wow. So it's not the 4 corners. Okay. So the idea doesn't work. Okay, well, what is interesting though is that we found kind of that you only need 1 or 2 cuts. It's just that it might not be. Are you okay? Okay. It might not be that you only need to consider the 4 corners. And here, yeah, this is an interesting position, right? Where this one has 2 connected ones. Interesting. What you can't do, I mean, one thing that would be inefficient is you try cutting once and then call number of islands and then, yeah. I mean, we could also do a parsing. Okay, first of all, if min-val, first of all, we made this assert. If min of values is equal to 1, whoops, min-val is equal to this, or say min-val if min-val is equal to 1, or min-val equals 2. Then return 1, right? And our idea was return 2 otherwise. But we might not always return 2. Right, we fail in the same test case. So we might not always return 2 in this case. So what can we do? We can, so one thing we noticed in that example here, right, is there is a column that is exactly 1, 1. So we can go through every column and every row. Right, so and we can populate this when we do number of islands, right? Or we can even do it here. Rows is equal to a dictionary. Calls is equal to a dictionary. I'm going to say I to empty list for I in range length grid, and then we know it's n by m, so we do I column for I in range length grid of 0. Then for, does this work? If I have s for I comma j in s, print I, print j. Can I do structure like that? No. For k and s, print k. Okay, I can't do structure like that in Python. For For pause in self.visited, row comma call equals pause, rows of row, these are going to be sets, actually it's just going to be the number of ones, right? So just need a 0. Self dot grid of row call is equal to 1, rows of row plus or equal 1, calls of call plus or equal 1. If min of rows dot values equals 1, or min of calls dot values is equal to 1, then return 1. Return 2. So I don't know, this might be a little janky solution, but the idea is that, like, if I find any row or any column that has exactly 1, 1, right? Like, for example, here this column has exactly 1, 1. Then my hypothesis is, okay, if I turn that into a 0, I just disconnected every one that was to the left and to the right of that, right? And we know there's at least 3 ones because we handled the case where visited is equal to length 1 and length 2, and length 0 and so on in case there's not one island. So if any row or any column has a singular 1, which is the only possible case, ideally, where one of the 4 corners might not be the one that has the minimum number of cuts, quote unquote, then I know that the solution is 1, right? If any row or any column has just 1, 1, meaning that every other element on that row or column is just water, then I know if I get rid of that piece of land, boom shakalaka, there it's like it's almost like this was a bridge, right? But then the point is, like, if there's more than one on that column, for example, then yeah, I could remove this one and I could remove this one. But just as well, I could have taken one of these corner cases, right, and made this a 0 and a 0. Again, we know that the maximum value here is going to be 2 because we can take any of these kind of corners, or like corners in the definition that I gave before, where it's where we know that we can at most do it in 2 days, right? But it could be that, like, if we have just a singular row or column where there is like that bridge connection, then we can just get rid of that connection and separate the islands, right? But again, even if there's just one more in that column, then yeah, this could be one of the optimal solutions, but we know of others that we could have already computed before. And then return 2. So I wonder if something like this works. No. Of course. Let's see. Okay, let's take something like this. Let's go L is equal to that. For L in L, we're going to say print this dot join string I for I in L. I'm missing a parenthesis. There we go. Okay, so let's look at this. What in Narnia is that? Where's the, so it expected a 1. So what 1 can we cut here? Okay, so it's the same idea again. Okay. Okay, so maybe we have to consider all of the ones where they are connected to at most 2 other ones, right? So yeah, now so okay, at this point of the problem, we know that the 4 corners are connected to 2 ones. So every other one in the problem is going to be connected to 2 ones at minimum. But now we should consider every other one, right? All the other ones that have exactly that. In fact, there are not that many, right? You can only have so much. I mean, you could do it for many columns and rows. Actually, is it true if you say something, if there is just any one that is connected to exactly 2 ones, that is not in the corners now, that means that, so if this one is connected, so what if this was a 0, right? So if that's a 0, and this one is connected to 2 ones, but right, so you need, so if there is a 1 and it's connected to 2 zeros, right? So that's the key point. Or not even that. It needs to be connected to at least 1 0. I mean, we could try. We could try a janky solution where we just go through all of them that have like exactly 2, set its value to 0, count the number of islands, and then it's like, oh, if it's greater than 1, just return, and so on. I'm trying to think if there's a more clever way to do this, because this is very interesting. So yeah, this one could have been here, and this could have been still a 0, and then this would have disconnected these 2 islands, right? But no, it's specifically, like, if you disconnected, you know, if this was a 0 as well. Yeah, that one's interesting. A little stumbling. So you just have to find if you can cut. But then it's like you don't know if when you cut it, like let's say you cut this one, right? And then all of a sudden there's this path, this path, this path, and this one happened to not be a 0, and then it's like, oh my goodness, you can visit everything again, right? Because like, okay, I have a solution in mind. It's just not pretty, right? It's just like you keep trying to delete these ones, quote unquote. Okay, well, first of all, we can consider just the ones. Okay. So one thing I want to do is we can consider just the ones that are connected to 2 others, 2 other ones. But one thing I want to do is, so my idea is like, for example, set this to 0, count the number of islands in the total graph, and then if it's 2, then yeah, return. Otherwise, reset it back to 1 and try it for another one like this. The only thing is that I know for sure if I do it on one of the corner elements, you will not, because at this point of the code, you will not have reached a point where the number of islands is more helpful to you there. So, okay, we can keep code like this. Otherwise, loop through all the ones in self.visited that have exactly two adjacent ones, except for the four cornermost ones, and then set its value in grid to 0, run number of islands, set back to 1 in grid, and return if number of islands call doesn't equal 1. Right, so that's kind of the idea. Okay. I didn't get rid of my code before, right? It was like this. Okay, we can do something like this. So first, find four cornermost ones to remove them from having number of islands expensive called upon them. So we're gonna say, yeah. It's gonna be leftmost column, and this is actually gonna be min of self.visited, where row comma call is equal to 0 comma 1. Each from leftmost and rightmost columns. Left row, left deepest row, comma right deepest row. Oh, actually, left topmost row, right topmost row equals what? Okay. Float infinity, float infinity. For pause and self.visited, I comma j equals pause. If j equals rightmost column, elif j equals leftmost column. Okay. So right deepest row and right topmost row. So okay, we're gonna put this here. So right topmost row is equal to min of right topmost row and I, right deepest row. Right, so we want the topmost row, so the one with the smallest value. So we start off at float infinity and that, then this is gonna be like that. Otherwise we do the same logic here, right? Rightmost row. Okay. corners equals leftmost column first of all, it's going to be left, 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 and left, left deepest row, leftmost column, then there's going to be the same thing, there's going to be right, right, and then here rightmost, rightmost, right? So these are our 4 quote-unquote corners, not actually corners, but like in terms of the island of ones that we have. Okay, now we want to take all the values from self.visited, take all values from self.visited, take all positions from self.visited that are not in 4 corners, and whose number of adjacent ones is exactly 2. So how does the filter work? So if I do d equals I comma random dot rand int 0 to 100, where I in range 50. Okay. Filter lambda x d of x modulo 2 equals 0, comma d. Predict of this. Maybe list. Okay. So I have a list of the positions, right? So yeah, 1 has the value is 80, 2 is even, 3 isn't, but 5 is okay. Yeah. So let's kind of use that idea. So yeah, okay. So this will give you us a list of the positions, right? Positions to check is equal to list of filter lambda pause. Okay, we're gonna do something like this. Filter lambda for, so we have a position. So we're gonna do self.visited. So what do we want the condition? We want it to be not in 4 corners. Pause not in 4 corners. And we want this to be an end condition. Essentially, we want self.visited of pause equal to, really should not be possible to be less than 2. And this for pause in positions to check. Self.grid, we're going to say I comma j equals pause. Self.grid of I and j, we're going to set it to 0. If self.number of islands doesn't equal 1, return 1. Otherwise, self.grid of I, j, we're going to set it back to equal to 1, and then we return 2. So now this should work. four corners. I messed that up, hey? Ay, ay, ay. Really? Okay, let's do something like this. Really? Oh. Prev visited set equals self visited. Copy. Self.visited equals prev visited set. Maybe that's why we're effing with the visited set here. So what the heck? We're already returning min val if it's equal to 1. Visited, print positions to check, print flag moment, and here return 2. Okay, this is debugging. Flag 2 moment. Lol. So 0, 0. Okay, first of all, remove these four corners. I'm pretty sure this is the case we had here. So 1, 0. So the only thing that might be uncool something like this is brute force and it should work. The only thing I'm thinking about it not working. First of all, assert self.grid of I j is equal to 1, but that should always be true. This is a lot of things to happen. Self.visited, but yeah, all these values are 2, 2. Let's use this as a test case. This is interesting. Okay. So clearly there's something wrong going with our number of islands here, right? I for I and self.visited. Assert prev visited set always equals self.visited. assert that length of prev visited set equals length of self.visited, and for element in prev visited set, first of all, we're going to put this in here. Assert L in self.visited. Oh yeah, is equal to this. We do not hit an assertion failure. Yeah, because we're only gonna add things to self.visited, right? Oh, but we're not gonna modify it, right? Assert equals I comma self.visited of I for I in self.visited. Self.visited of L equals prev visited set of L. Wow. So that's very interesting, right? Because here, what's the index that we want to deal with, right? 0, 1, 2, 4, 5, 0, 1, 2. So we want 5 and 2. Why is 5 and 2 not here? If I do 5, 2, 5, 2 is 3. 0, 1, 2, 3, 4, 5, 0, 1, 2. Or 3 and 2. What? How is this wrong? I plus di and j plus dj. Di comma dj. Okay, I'm not messing these up. Okay. Yeah, so this is 0, 0. 0, 1, 2, 3. 0, 1, 2. This is 3 and 2. This should be 2 adjacent ones. Yeah, for each one that's next to it, if it's in bounds and its value is 1, add 1. And comma 5, 2. j. What the heck? Print new I, comma new j. New I, new j. Oh yeah, sorry. Sorry. Okay. New I, new j. Let's just print that. Yeah, if this, then we're gonna print it. So it says 4, 2, 5, 1, and 5, 3. So if this is 5, 2, this is 4, 2, which, why is 4, 2 in here? It is all 4 directions, right? Negative 1 and 1. Negative 1 and 1. Right. Well, this I agree. 5 and 1. 5 and 3 are both 1. Why is this being counted as a 1? Okay, we're gonna say def print grid self for I, for row in self.grid, print this dot join string of I for I in row. So here we're gonna call self.print grid. Print self.grid out 4 and 2. One. 0, 1, 2, 3, 4. 0, 1, 2. Dude. How? What? Oh, unless I'm thinking about it wrong. And oh my goodness. So is this 0, 1, 2, 3, 4. So okay, so this is 0, 1, 2, 0, 1, 2, 3, 4, 5. So this is element 2, 5. Okay. So this is 2, 5, and what? This is 2, 3. Okay, 2, comma 3. Okay, 2, 5, and 2, 3 are here. Okay, so we can get rid of all that. So this we can get rid of. This we can get rid of. This is just very annoying. It's only gonna be when, yeah, you're gonna have to run something like number of islands, right? Because it's like, before in this case, it's like, just because this is connected to 2 zeros, you have no idea if it doesn't mean that you can still loop around to this other island some other way, right? So, you need, you do need to call something like number of islands, and you can't rely on something like DFS BFS because, well, yeah, you're not gonna know which elements of the island are enclosed to that one and so on. So you just have to compute the number of islands after you change something like that. But the only thing is then, why is this not correctly computing it, right? Where self.number of islands. Oh yeah. When I say positions to check is equal to just 2, 3. Then what if we run this? Really? Got here. Oh my goodness, no way. Why do I return 2 here? Are you for real? There's no way. Oh my goodness. Okay, now this is weird though. Oh my goodness, that's so silly. We were preemptively returning 2. Yeah, let me run this and see if it works. Doesn't. Output 1 and expected 2. Oh, so now it's the opposite problem. Okay. Maybe if we get rid of something like the 4 corners. Now we actually pass less with that. Okay, so here we still have a return 2, which is good. Oh yeah, we're not going to modify self.visit because we always check if something is... Oh! Wait, that could explain it actually. That could explain it. Self.visited.clear. Now we should run into these assertion errors. Yeah. Self.visited is equal to prev visited set. Aha! And now does that work? 98 out of 99, are you serious? Okay. Okay, well we're closer than we've ever been before, so that's good. 0. Okay. Let's think of this case. 0, 1, 1. So what's the output and what's the expected? Okay. 1, 1, 1, 1, 1, 0. Oh, are you serious? This one is connected to 4 1s, but it can be the one that's used to... Nah, that's illegal. Are we just seriously gonna have to run... Dude, I refuse this. We're gonna have to run self-number of islands on every single freaking one. That's so unbelievably frustrating. Okay, So basically what I'm realizing is you can do a quick bunch of shortcuts in order to realize if there is a solution that is just one. But otherwise, if not, so that those shortcuts involve like checking if the four corners have one of those solutions, checking if exactly one of the rows or one of the columns has exactly one, and so on and that. And you invest a lot of time in finding if any of those shortcuts work. Otherwise, your best bet is just to do set.number of islands. Asymptotic complexity wise, like your best bet is just to do set.number of islands straight up and so on, so you don't waste the work in case the answer you return is 2. But yeah, okay. Well, that just gave us a case where you can have a 1, but then again, it's just like if it happens to exactly... Okay, wait, we can actually do this, right? So that one happened to be on a diagonal. So we check if a row has only 1, 1. If we check if a column has only 1, 1. Wait, so if a column or a row has only 1, 1. What if a diagonal has only 1, 1? We can actually check that. So both the positive and negative diagonal, right? So this is again greedy. Rows, diags. We're going to do ooh, wait, do we have to do every positive diagonal? Mate. Yeah, if any diagonal that is not the trivial corners. How can we map an index I to a diagonal? So maybe it's like if we have something like, what do we have before? Let's see, L is equal to this. Well, now this, there we go. So maybe it's like diagonal that goes from here. So each of the positive diagonals from these indices, right? But then there's positive diagonals from these indices as well. So there's all these positive diagonals. I remember in a problem like N Queens by LeetCode, he had a way of uniquely mapping each positive diagonal and each negative diagonal, where it's like, think about it, okay, if you come from here and you go up here, you decrement the number of rows and you increment the number of columns, right? So it's like the number is fixed. Here, right, it's 0, 0, but then there's nothing else, because then you have -1 and 1 and so on. So then the number 1 would map to this diagonal, right? Because it's like here the row number is 1 and so, okay. And so then it's like, then this one is, so the deepest one is going to be R plus N, right? So you're going to have positive diags is equal to I0 for I in range length rows plus length columns. And then same thing for negative diags. I0 for I in range length rows plus length columns. Or actually for those, what are the negative diagonals going to be? So it's going to be 0, so if 0 maps to this, so what does this get mapped as? -1? So the idea is like, okay, you always increment by 2, or no, you increment the number of columns and you increment the number of rows. So how do you, for negative diagonals, how would you uniquely map them? Wow. So you know if an element if you take a value like this, or a value like this, you know it's on this negative diagonal. Why? 0, 1, 2, 3, 4, 5, 6, 6 and 2, 6 and 2, 5 and 1, 4 and 0. Oh, if one minus the other gives you the same number? Zero, 1, 2, 3, 4. So yeah, it could be like that, right? So this is like what? Row minus col. It's what, like row plus col? So like for this one, this positive diagonal is the one that happens at 4, which is number of rows plus number of column. Okay, okay. So maybe we can do positive diagonals. So if we're at index row and col, so we're going to say of row plus column. And so this is going to be actually, so we want from 0, so we want from negative column, all the way up to row. Right, so row could be 0 and you have column. So you want this 1 minus column. So maybe I plus 1 for this, right? So yeah, you can't have yeah, this makes sense. Okay, so this will be positive diagonals will be row plus column, and then negative diagonals is equal to of row minus column. These are going to be plus or equal to 1, plus or equal to 1. So then this is going to be a huge if statement. I pray this works now. Or min pos diags dot values is equal to 1, or min of negative diags dot values is equal to 1, then return 1. Now let's use that as a test case. Whoa. Negative, yeah. So length of calls minus 1, which ends up being plus 1. So this plus 1 all the way up to length rows, negative length calls, length rows. Let's try that. That one doesn't work still. But that should work, right? So it's like this element is clearly inside this negative diagonal. Or wait, am I crazy? Here, here, here. Oh yeah, it's m by n. This is 0. So it's 1, 2, 3, 4. It's in the 0 negative diagonal. Maybe this only works for n by n. Okay, so we can scrap that idea. Yeah, it would be nice if we can map every diagonal to a specific number, right? But I'm sort of failing here. So maybe additional positions to check. going to be equal to this filter is greater than 2. Plus additional positions to check. Maybe that'll work. Positive diagonals. Okay, that works. Okay, and that's it for the problem. I mean, of course, yeah, this solution is just now terribly slow, right? That's just that's really, that's such a bummer. There must be a way, yeah, there like I suppose there must be a way to just do the diagonal trick and so on. It's just I'm not figuring it out, right? Or maybe we can do 3s is equal to when this is equal to 3. 4s is equal to greater or equal to 4. To be greater than 4. And here we're going to do plus 3s plus 4s. So I essentially want them in order of like greediness, right? So it's like, oh, if you went through all the 2s, then yeah, it's just not gonna help our asymptotic complexity. Oh well. I mean, yeah, that's just a huge bummer. At least, okay, at least it passes the test case. I can't really figure out a way to do it otherwise. Okay, I'm just gonna get rid of this function. Now we're just gonna do a little bit of code cleanup. So let's get rid of all these debug statements. Chuka chuka. Yep, that looks good. So this one looks good. Then we can get rid of this. Up, down, left, right. Yeah, that's fine. Get rid of that guy. Yeah, so yeah, this was our old code that we just decided to get rid of. Tac. Yep, this we can get rid of. Zero. Number of islands call. Yep. Yep. 3s, 4s. Positions to check is greedy, but might also need to check all the other ones as possible for rare cases. Yeah, I'm kind of bummed because I'm pretty sure if I figured out the logic for how to map each unique positive and negative diagonal to a unique value, then I could solve the problem straight up without having to call number of islands every single time. Yeah. Maybe we can do something like that. Map diagonal to unique number in m by n grid. Yeah, okay, it's just, yeah, okay. It would take a little long to search. Okay, no worries. For now, we can just clean this up. But yeah, that's just a little bit of a bummer for now. Positions to check is greedy, but might also need to check for all other ones. It's possible in rare cases they removing them actually disconnects the island. Yep. And we're gonna wrap this in quotes. Yeah, at the four corners. Honestly, we can get rid of this. And then get rid of the four corners logic. It's just not worth it. It technically is, but whatever. Well, you know what? It can only make our code faster, so why not? Okay. IJ pause. Yep. Yep. Can get rid of these two. Get rid of these two. Get rid of these two. And these come at pairs. Position pairs. Okay. Okay. Otherwise, yeah, let's just submit one more time. Okay, yeah, our asymptotic complexity isn't going to change or anything and so on. Okay, otherwise, that's essentially it for the problem. As always, I'll do a quick recap of how I solved this problem just to get as a quick summary at the end of the video. So essentially here in this problem, we're given a grid and it has a certain number of islands, right? Kind of in a problem like number of islands, where an island is just defined as four directionally connected group of ones. So here, like these ones are connected together and so on, but here they're not connected together because there's no way to get from this one to this one by going in left, right, up, or down directions within a sequence of connected ones, right? So if this one was also a 0, then these three ones would form an island because they are all reachable by going in an up, down, left, or right direction, right? And so this problem asks, given that you can convert a 1 cell into a 0 cell, so a land cell into a water cell, every single day, how many times does it take to make the graph disconnected? So a graph is only connected if there is exactly one island. So the very first thing I did in this problem is I count the number of islands in the graph. And first of all, if the number of islands is not equal to 1, that means the graph is already disconnected, so I return 0 days, right? You don't need to waste any days. The graph is already disconnected. Otherwise, there is exactly one island. And one thing that I realized is that in the very worst case, you have one island of ones, and if you go to the rightmost column in grid that contains a 1, and you go to the bottommost one inside of that column, then necessarily, because it is the bottommost one, it will have no ones below it, and since it's the one on the rightmost column that contains ones, then it will be no 1 to the right of it. So there's either a 1 to the left and above, or only 1 to the left or above of that 1, right? If there is only 1 that's to the left or above of that 1, then the number of days it'll take is just 1, because it's like this one here, you know that it's impossible for there to be a 1 to the right of it and beyond. And you know that it's impossible for there to be a 1 below it and beyond. So then you ask yourself, okay, what can be above it here, right? Whoops. what can be above it here, and what can be to the left of it here, right? So those are kind of the questions that you have to ask yourself. And so first of all, if at least just one of them is not a 1, well, first of all, we know the other one is a 1 because there is one total island, right? So first of all, if there's not just one island, then we return directly from the problem. And also I hard-coded the case where it's like, if the number of ones inside that one island is 1, then just return 1 because you can replace that 1 to water. Or if it's 2, exactly 2, like in this case, then you have to invest into making them both water, because if you delete one, the other one will be now the complete island and you have to get rid of it. So besides these two cases, I assume there is more than 2 ones inside of the problem, right? And in that case, that means that since there is one island, at least one of these question marks that are here, right, must be a 1. Without loss of generality, let's assume it's this one, right? Then, if this one is a 1, then I know for sure if I convert this one into a 0 and this one into a 0, in 2 days, I will have isolated this one from any other one in the problem. And there must now only be, like this one cannot be connected to all the other ones, and therefore there is now 2 disconnected islands in the problem, and therefore we're done with the problem. So we know that there is a theoretical maximum now of 2 days in order to solve the problem, right? And so we know that if there is one island, you will have to do at most 1 replacement, right? So if one of these is a 0 and the other one is a 1, then you just know that if you replace this to a 0, bada boom shakalaka, you're done with the problem. And because this one is now disconnected from all the other ones, like let's say there's a 1 right here, and you're done with the problem, right? Now the tricky part is when for inside of this corner there's 2 1s. Well, what if one of the other ones in the problem, like kind of like here in this example, what if all of these corners, right? So in the rightmost column, bottommost 1, same thing for topmost on the right, topmost on the left, and bottommost on the left. What if all of these is connected by 2 1s like this, but there happens to exist another one in the problem such that if you made it a 0, you'd actually disconnect the islands, right? Here it would be like this plus this. If you make this a 0, would be disconnected because there's kind of the 0 here, 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 right? And so what I did essentially is just it's very inefficient, and I thought of a more efficient way earlier, but I don't want this problem to get too long and so on. So I'll just leave it as is for now. But the idea is just the trivial thing. It's you come from this one, you go through every single one inside of this huge matrix, and for each of them, what you're gonna do is, okay, set it to 0, then from this new grid, compute the number of islands. If the number of islands is now larger than 1, or not 1, and so on, whatever, then you're done with the problem, right? Because you've officially disconnected the full thing, whether it's because there's 0 islands or more than 1 island now. Otherwise, set it back to a 1 and try with another 1. And then if you've done that with every single one in the problem, and for every single one, deleting them did not make disconnect the island, then you know that the solution is 2, right? Because again, from then you could also try every one and try every pair of 2 1s and then see, like, calls out the number of islands and so on. The reason you don't have to do that is because you have these corners, right? And you know for each of them that it's gonna take at most 2 days in order to disconnect them from the rest of the island. So you have a theoretical max, and now you just have a theoretical minimum of like, oh, what if deleting one? What if replacing one of the other ones makes it so that it only takes 1 day in order to disconnect the grid? Well, that's why you have to check all the other ones. But you don't have to do this like for every pairs of 1s after that, and every triplets of 1s and every quadruplets of 1s, because you know that there is a theoretical max of 2 days given the corner cases, right? And the island doesn't have to be like a nice square or a nice rectangle, right? They can be something like you have 0 0 0 0 0 0 0 0 0 0 0 1 here, and then here there also happens to be a 1. Like this would be the bottommost rightmost one, right? Because here there might be more zeros. It is the rightmost column that contains 1s, and this inside that column it is the bottommost one, right? So that would be my bottom right corner 1, even though obviously there might be like way more elements over here and so on. It's not the actual bottom row and so on. So it's just kind of my own unique definition corner ones, right? They don't have to be on the legitimate literal corner. But for those corner ones, you know there's a theoretical maximum of 2 days in order to disconnect them from the rest of the island. So you know the maximum value you can return for this problem is 2. And then it can also be 0, in which case that's a trivial case where if you call number of islands and there was not one island to begin with, then you know you're done with the problem. So the hard part is when there's only one. And I did a bunch of like ninja tricks where it's like, okay, I first check if any of the 4 corners can be done in time and etc. blah blah blah, or I check if like exactly one row or one column has 1 1. So obviously getting rid of that one would what's it called? It would just like disconnect the 2 graphs. But obviously at the end of the day, it's like if none of those ninja little shortening tricks work, then you're just gonna have to call number of islands on every single number 1 and replace it with 0, call number of islands. If it disconnected the graph, then great, just return that value, and then return 1, I should say, and then otherwise reset it back to 1 from 0, and then try with another 1. And then if any of those happen to return 1, then that return that self-done like number of islands is greater than 1, then great, you just return 1. Otherwise, that means you've exhausted every single possible 1, and for each of them you've noticed that replacing it with water did not disconnect the graph, and so you just return 2 because again that's the theoretical max that we were talking about. And that's kind of how I went about solving this problem. So again, this problem is very similar to yesterday in the sense that it really required knowledge of knowing how to do number of islands. So if you have never done that problem before, I guess, okay, I understand why this is a LeetCode hard now, where it's like it builds on top of the idea of number of islands. So if you've never solved a problem like number of islands, this problem would be hard, right? So it's just like connecting multiple mediums. But if you know something like number of islands beforehand, this problem is not too challenging if you think a little bit about it. But yeah, otherwise that's essentially it for today's video. I hope that little explanation did make some sense. I know it was a little bit complicated, but otherwise, if you want to end up doing something similar to what I do, the extension that I use is called LeetSync. I trust this extension, but by no means do you have to trust this extension yourself. What these guys do is every time you submit a problem on LeetCode, like here, like by pressing the submit button, they will automatically push that code that you just submitted into your GitHub repository and make it very, very convenient to access your solutions all in one place. So here, for example, if I go into my GitHub and I come into my LeetCode folder and I Control F for minimum number, is it not called minimum? Oh yeah, it is. Minimum number of days. So yeah, you'll see now is when it was just committed. And so it'll commit a copy of the README to the problem, which you'll see was 17 minutes ago, because it'll do that on your first valid success on LeetCode. And then every time you resubmit a new solution, it'll just re-upload it here. So if we take a look, again, this is just the solution that I just came up with here inside of the problem. So yeah, maybe I can remove these little comments over here, which are not too helpful, but otherwise resubmit that. And just as a little proof, once that's done submitting, I can refresh this and you'll see, yeah, you got rid of the little comments that I had here. So very, very useful extension in case you want to do something similar to what I do. But again, just because I trust this extension doesn't mean that you should automatically trust this extension yourself. So use at your own risk. But otherwise, that's pretty much it for today's video. I really appreciate you watching. If you did find this video useful or enjoyable, I would highly appreciate if you left a like or a comment. If you take the time to leave a comment, I promise I will respond to every single comment on my channel while I still can. And otherwise, I will catch you in the next one. And so until then, ciao, ciao, my friend. Thank you.